Hi, this is Eitan Zinberg. This is CS6963 Digital Forensics. This is my final project. So I did my final project on steganography and Steganalysis, which is the method of hiding messages in other files, and Steganalysis is the detecting of those hidden messages. So I specifically wanted to do my project on these techniques with regards to audio files. There's been a lot of literature written about how they apply to image files, not quite as much on audio files, and I wanted to do twofold. First of all, build a useful program that can perform basic steganography with audio files. Then I did some research. I wanted to implement one of the techniques of Steganalysis when it comes to audio files. I'll describe quickly essentially what it does, how the program works, and then I want to walk through the code. So the code takes advantage of something called least significant bit technique of encoding a file in another file. So the idea is that the least significant bit of an audio frame is not going to be significant to the human ear, and you can change it without the human being able to perceive it as an audio difference. So we can encode a long text file as in the ASCII values of bit by bit, one bit into each frame of the audio. The audio files have quite a lot of frames that they save, and we can take advantage of one bit from each frame, and we can encode a long message. Some of this code, the sound class is based on code found online put out by Blake O'Hare, and the basic structure of the program is based on Stegalize, which is a program written by Mark Budowski in 2010, I believe it was. So just to walk through it. So we have, here's the main, we have all of our options. We have an encode option, we have a decode option, and we have our analyze option. Those are going to be the three important ones, and we'll get to the encrypt and the random in a minute. Essentially, you can, I'll just show you how it works. You can have, we have Python. This is written in Python 2.7. And if we want to encode, we put the E flag, and I want to encode into I have an audio file saved here already called audio.wave. This module is this program is specifically for .wave files, and you could either put in a text here, or I have a text file saved here called short text.txt, and it's encoded into you could see now there's a new file, segaudio.wave, where if you actually open up a hex editor, you could see that the bits have been changed, and then you could go and again we have our program, and this time we're going to give it the decode flag, and we're going to give it the new file, which is now the Stego audio, and it actually gives us the Gettysburg address, which is what I have saved into the short text. And a couple of the other options that I have here, right? Just to go into the actual code itself, you have in the encode right over here at the top, you could see that the way it's encoding this is over here for each a letter, you're going to have by ending with 1 and shifting the bits, you get each individual bit and you save it into the least significant bit of an audio frame. There are a couple other options that are provided here that you can encrypt it. It's going to use a Visionary cipher to encrypt it if you don't want the ASCII values of your text file stored directly in the file, and then you would need a secret key in order to recover it. And we also have an option of putting it in a pseudo-random order. If you give it a random key, it'll use that as a seed for a pseudo-random generator to put it in a random order into the file. That way, even if someone knew that you were using the file for steganography, they still would not be able to recover your text without having the random key, and if you encrypted it without the encrypted key. Just to demonstrate that, we can encrypt it and we encode it with an encryption key. Right, we could just call it encryption key. And then if we don't provide that encryption key, we'll just get back gibberish. The second part of my project that I attempted to do was do a Steganalysis technique based on a paper written by 3 researchers from China back in 2013. Essentially takes advantage of high dimensional feature extraction. They attempt to show that that all audio files are essentially the voice plus noise, and that noise can be the environment noise, or it can be, in a case where you're using the file for steganography, it could be based on noise created by changing the least significant bits. So they attempt to show that if you use 2 different methods to extract the noise, so then you can analyze the noise, and you could use that to detect whether the file is being used for steganography. So the 2 methods that they have is, one is wavelet denoising and the other is local correlation. A little bit complicated, the wavelet denoising, but essentially they take advantage of a technique that from JPEG 2000 to essentially, the point is there's an algorithm that they use to separate it into high and low frequency. Once it's decomposed into that, then they could clean up some of the high frequency noise before reconstructing it, and that essentially removes the noise. So then if you subtract that noise, the file without the noise from the original file, you can isolate the noise, and that noise will be made up of both the environment noise and whatever changes you made to it. And the second method that they have is local correlation, that most change from frame to frame is not going to be the voice that changes, it's going to be the noise that changes. So again, if you subtract 1 frame from the previous frame, you'll get just the noise. And once they isolate the noise, they use a second order Markov model to try and see what the probability of a least significant bit being either a 1 or a 0 based on the previous couple being that same thing. So essentially I attempted to code this, to create a tool to be able to use this. So you have this one is to deconstruct the wave, then cut away the noise before reconstructing it, and then I have my the local correlation method, and then this double Markov is going to be the probability. It's going to attempt to analyze it. So if we were to analyze this file that we created with our analyze flag, so we have this will give us the Markov probability for the two different methods. One is giving us around the 50%, the other one's giving us the 65%. This is only because the audio that I was using was provided from the microphone. That's why this one is even this high, 65%. Unfortunately, the method did not seem to be producing the same result as it produced for the three researchers. Pretty much regardless, it was giving me in the range of 50%, meaning that there's no predictability of the next least significant bit based on the previous frames. That's it.